Hello students, we are ready with our next video. In this video we will discuss the factors which are responsible for altering the changing the delta value of different protons. There are three main factors which can affect the delta value. First factor is electronegativity of the element through which proton or carbon is attached. Second factor is the state of hybridization. What is the state of hybridization, whether it is sp3, whether it is sp2, whether it is sp. And third is the effect which is known as anisotropic effect. I will discuss these three effects one by one. But before that, I just start with my first factor, but the electronegativity. I told you in the initial classes that higher is the electronegativity of the element through which proton is attached, higher will be the de-shielding, and higher should be the delta value of compound, or delta value of the protons. So as you increase the electronegativity, you increase the tendency of the element to attract the electron toward itself and making the electron cloud around the proton lesser and lesser. So you make the electron cloud lesser and lesser, it means you cause the de-shielding. De-shielding means removal of electron cloud is called the de-shielding. You're stopping the shielding. So as you increase the de-shielding, you make your proton more exposed to the external magnetic field, and more exposed means higher precision frequency it will experience and higher delta value it will show. So in simple word, I can say that higher is the electronegativity of the element through which proton is attached, higher should be the delta value of that proton. So I am taking different example. You can see here methyl iodide, methyl bromide, methyl chloride, methyl fluoride. We are increasing in this direction as we consider the electronegativity. So this methyl proton delta value should be we can observing here is 2.16, 2.65, 3.10, 4.26. So as we are increasing from less electronegative element to the high electronegative element fluoro, from iodide to fluoro we are moving from less to higher electronegative element. So we are increasing toward higher and higher delta value. You can see here it is methane, it is chloromethane, it is chloromethylene, it is chloroform. So as the number of electronegative element also increases, here it is 1, it is 2, it is 3. So as the number of electronegative element increases, more is the de-shielding will be observed. So as the number increase, more de-shielding will be observed, and hence higher delta value should be observed. So delta value of methane is 0.9, chloro 3.05, dichloro 5.30, trichloro 7.27. So as the electronegativity increases, delta value increases. As the number of electronegative element increases, delta value also increases. The third factor is the distance. Suppose I'm considering the delta value of this methylene proton. So in this case, bromo is very close, so delta value is very high, 3.3. In this case, it is separated by 1 CH3, so delta value is 1.63 of this methylene proton. In this case, it is separated by 2 CH2 because bromo is far away from the methylene which we are considering. So in this case, the delta value is least, it is 1.25. So as the distance from the carbon atom in consideration increases, the delta value should decrease. Third factor is the fluoro. As you can see here, it is a fluoro derivative attached with the carbon through which the proton is attached. Value is 4.2. It is a oxygen attached to a carbon through which hydrogen is attached. Value is 3.3. It is nitrogen and carbon through which proton is attached. Value is 3. So as you can see here, fluoro is the most electronegative elements, then oxygen, then nitrogen, and hence should be the order of delta value. Higher is the electronegativity, higher should be the delta value. Higher is the distance, lesser should be the delta value. Higher is the number of electronegative element, higher should be the delta value. It is these three factors, these three consideration points should be clear in all of us minds. The next factor which affects the delta value is the state of hybridization of the atom through which proton is attached. There are three states of hybridization which we know: sp3, sp2, and sp. If I ask you to find out the percentage of s character, so to determining the percentage of s character, what we do? In case of sp3 hybridized orbital, there is one s out of 4, so percentage is 25%. In case of sp2 hybridized orbital, there is one s out of 3 total orbital, so percentage is 33%. In case of sp hybridized orbital, there is one s orbital out of 2 or total orbital, so percentage is 50%. Remember, more is the s character, more is the s character, more is the electronegativity. Electronegativity. Higher is the s character, higher is the electronegativity, because s orbital are found to be closer to the nucleus. So more is the s character, it means electrons are very tightly held by the nucleus and protons should be de-shielded. I repeat it again, more is the s character, s orbitals are closer to the nucleus, so more is the s character of any carbon, then its electron should be very tightly held by the nucleus. So the proton attached with this carbon should be one which is very de-shielded. So higher is the s character, higher is the de-shielding. So in that case, so we should expect the order of the delta value should be sp3, sp2 and sp. But we are observing 0 to 2 from sp3, 4.5 to 6 for sp2 and 1.5 to 3.5 for sp. So we are observing a altered we can say a altered order of the delta value, because the sp should be expected, it is expected to be the highest, but it is not highest, it is occurring at a middle value. So we can observe here what we actually observe. So what we actually observe is that sp, which should be the highest, show us the highest delta value, is showing us the intermediate value. So actual order is sp3, sp, and highest is sp2. This is the actual order of the state of hybridization and this actual order of the delta value. Why this sp show us less delta value and why this sp2 show us a high delta value can be explained by the another important factor. This factor is called anisotropic effect. Anisotropic effect is the third factor which will explain why anisotropic effect will explain why sp2 are having high delta value and sp3 are having sp2 are having high delta value and sp is having less delta value. It will be explained by the third factor which is called the anisotropic effect. But before moving toward the anisotropic effect, if I ask you one question in your exam, like I ask you a very simple question in your exam, suppose carrying 1 mark, and I ask you out of these two compounds which one is expected to be of higher delta value. So high delta value should be of this, because in this case all our carbon atom is sp2 hybridized. So each proton should be showing high de-shielding, but in this case every carbon atom is sp3 hybridized, so it is less de-shielded, so lesser value in this case, so less value in this case and high value in case of sp2 hybridized orbital. So this should be clear to all of you that sp2 is showing a higher value than sp and sp3 hybridized orbital. But why it is showing higher value can be explained by not only by state of hybridization. One factor is the state of hybridization which explain their order. The another factor is there, and then that another factor is anisotropic effect, which I will explain in just a few minutes. Anisotropic effect is an effect which is observed in case of all those compounds which contain loosely held electrons, and loosely held electrons are pi electrons. So the anisotropic effects are observed in those compounds which contain pi electron or pi bonds. So we can think of anisotropic effect in case of alkene, we can think of anisotropic effect in case of alkyne, we can think anisotropic effect in case of aromatic compounds, we can think anisotropic effect in case of aldehydic compound mainly, but alkane is also shows anisotropic effect, but mainly alkane also shows anisotropic effect, but mainly we consider anisotropic effect in alkene, alkyne and aldehyde type of compound. What is this effect? In this effect, when we take any compound which contain double bond, which contain pi electron, and we introduce this compound to the external magnetic field, so in that case the loosely held pi electrons start circulating in a certain direction, in a particular direction, and when they start moving or circulating in a particular direction, the loosely held electrons, the pi electrons, generate two type of field, two type of environment around their molecule, and these two type of environments are de-shielded environment and shielded environments. So I repeat again, when any pi electron containing compound starts circulating, it is exposed to a external magnetic field. The pi electron starts circulating in a very particular direction, and when they start circulating in a particular direction, they generate the secondary magnetic field, and this secondary magnetic field generate two type of environment around the whole molecule. This type of environment is de-shielded environment and shielded environment. If proton under consideration falls under de-shielded environment, it will be showing us a high delta value. If a proton falls in a shielded environment, it will show us a lesser delta value. So it is just an anisotropic effect. So anisotropic effect is exposure to the magnetic field, circulation of electron, generation of two type of environment, one de-shielded and second is de-shielded. I'm explaining the concept on alkene molecule. Suppose this is alkene molecule, this is the applied magnetic field. I'm taking alkene molecule as this, as a CH. Two protons are toward the viewer and two protons away from the viewer. So this is the plane of alkene molecule, CH, and we are applying magnetic field perpendicular to this plane of this alkene molecule. We are applying magnetic field from here. So what happened in this case? The cloud of electron, the above cloud of electrons of pi electrons and lower cloud of pi electron start circulating. I repeat again, the above cloud of electrons and lower cloud of electrons start circulating around the this alkene molecule, as I am showing here. They start circulating around the molecule and generate a type of a cone. I can say this is a cone. This is after circulation, the protons which are found in cones, are found to be de-shielded. Again, this alkene generates two type of environment. First is shielded environment and second is de-shielded environment. So if I have to draw it as a cone, I have to show it as a cone. Protons which are lying here, which may lie here, are found to be shielded. Which lie inside this cone, are found to be de-shielded. So inside the cone, de-shielded environment is generated, and inside the cones, protons are found. This is the reason why alkene protons are found to be de-shielded, and they show higher delta value. So there are two factors for alkene to show high delta value. First is the state of hybridization, and second factor, another important factor, is the anisotropic effect, through which a region in which protons are found are one where de-shielded region is generated by the anisotropic effect, by the circulation of the loosely held electron. This is the molecule. The loosely held electron start circulating, and when they circulate, they generate in this region, they generate shielded region, and in a cone they generate de-shielded region, and protons of this olefin molecule are found in the cones, so they are in the de-shielded region, and hence they show high delta value. So this is the case of alkene system. This is the case of aldehyde compound or any carbonyl compound. As you can see here, in carbonyl compound we have a C, H, and O. State of hybridization again is sp2, and we can show a cone of aldehyde compound like this, passing through oxygen atom to generate a cone. And again here we are having aldehyde compound like this. This is CO, this is CH, this is CH, and we are passing the magnetic field at the angle of 90 degree to the plane of aldehyde molecule. So this is aldehyde molecule, this is carbon, oxygen, CH, and this is the magnetic field passing at the angle of 90 degree to the plane of the aldehyde molecule. In that case, the pi electron above and below the ring will start circulating in a particular manner, and particular manner will generate a magnetic field in a very circular motion around this molecule. So in circular motion here and in this motion, it will be shielded effect. A region will be shielded, but if we generate the cones of this molecule, then this is the above and below the region we are observing shielded effect. But if we generate the cone, we make the cone of this molecule So we can say those atoms which are falling inside the cones are found to be de-shielded. So de-shieldings are observed. So in the cone region, de-shielding is observed. So protons are found in a cone region. As you can see here, proton of these two are found in a cone region, so they are de-shielded. But above and below, they are shielded region, because above is the circular motion. Above is the pi electron, below is the pi electron. They're moving in a circular motion. So above and below there is a shielded, but in a cone, if you consider the cone, in cone the molecule are found to be de-shielded. The proton are found to be de-shielded. So in case of aldehyde, there are two factors for a very high value. Aldehyde protons shows a high value, approximately 6 to 9. Why delta value is so high? There are two factors for this. First is the anisotropic effect, because these protons falls in a de-shielded region, and de-shielded region means a region where delta value is very high. And the second factor is electronegativity of CO. This CO withdraw the electron toward itself and make the protons again less shielded, or make the proton de-shielded, and hence these protons observe a very effective de-shielding due to electron withdrawal by the CO and electron de-shielded environment by the anisotropic effect. So these two effects are responsible for high delta value in case of aldehyde. This is the case of aromatic compound. Aromatic plane, this is benzene plane. This is my palm is the plane of benzene. So in the, I'm applying magnetic field from below the plane of this molecule. When I apply a magnetic field in this way, so the again pi electron cloud above and below the ring will start circulating in a particular fashion, and this circulating in a particular fashion. So above and below the ring we will be observing shielded region. Above and below we will be observing shielded region, but inside the ring, this is the above, this is the cloud, but inside the cloud there is a proton, and proton will be in a de-shielded region. And we can say that this generation of electron cloud, this movement of electron cloud around the aromatic compound will generate above and below the ring will generate a cloud, and this cloud, when a region inside the cloud will be shielded, but region inside the cloud where proton lies are where de-shielded region is generated. So proton are found to be de-shielded in case of aromatic compound. So here again aromatic compound de-shielded by two factors. First, there is high value, again 6.5 to 8 delta values observed for aromatic compound proton. So there are again two factors. First is the anisotropic effect, and second is the sp2 state of hybridization of CH carbon. So these are the two factors which are responsible for the high electronegativity, responsible for the high delta value of the aromatic compound. First is the anisotropic effect, and second is the sp2 state of hybridization of the carbon. The next molecule is alkyne. In case of alkyne, there are sp hybridization, and we have two pair of we can say the free orbital, the pi electron. One is pz, one is py. So we have a bulkier electron cloud in case of alkyne system. So in case of alkyne system, suppose this is the alkyne molecule CH, triple bond CCH, and we pass the magnetic field along the axis of the alkyne molecule. In this case, the magnetic field generate around this is the alkyne molecule, this is the CH, CH, and we pass a magnetic field from below. So in this case, the magnetic field is generated around the molecule by circulation of electric field, by the circulation of the electron cloud. So when they circulate in this fashion, so they generate again a cone, and in this cone, as you can see here, the electron cloud which are lying inside the cone are found to be de-shielded, are found to be shielded. I'm sorry, electron, you can see here, this is pi, this is the CH, triple bond CH. So as we make the cone of this alkyne molecule and pass the magnetic field along the axis of alkyne molecule, and they start showing us the magnetic the circulation of electrons. And when we generate the cones, the region inside the cones are found to be shielded. The region inside the cone are found to be shielded, and the inside the cone region is also the region where protons are found. So you can see here protons are found inside the cone region. So in this case we can say that protons are exposed to a shielded region. But out above and below the cone we are observing a de-shielded region. But in this de-shielded region there is no proton. Our protons are lying in a cone, and cone are experiencing a shielded. Cones in case of alkyne are experiencing the shielded region, and due to shielding, as the name suggests, shielding, electrons are shielded, the cloud of electrons are shielded the protons, and more is the shielding, less is the exposure to the external magnetic field, and less will be the precision frequency, and less will be the delta value. So more is the shielding, lesser the delta value. So in this case of alkyne system, they are more shielded, and hence they have a lesser delta value. Delta value in case of alkyne are found to be lesser than even alkene. They are found to be approximately from 1.5 to 3.5. It is only due to the reason of anisotropic effect. So this is question usually asked in your exam. So I carrying approximately 2 marks, which ask explain the order of the proton delta value in case of alkane, and alkyne. So you have to explain this on the basis of anisotropic effect, that alkane is least, then we have alkyne, then we have alkene. So this is how we explain why anisotropic effect is responsible for high delta value of aldehyde, high delta value of aromatic compound, and less delta value of alkyne. So on this effect we can explain why alkene have a very high electronegativity and very high delta value, and why alkyne have a less delta value, and why aldehyde and aromatic compound have a high delta value, because this is only because of the anisotropic effect. But in case of aldehyde there is a CO, electron withdrawing by the CO, that is also important responsible. In case of aromatic compound there is an anisotropic effect plus sp2 state of hybridization, that is the second factor. But in case of alkyne in case of bialkyne, alkyne have a less value, because anisotropic effect make the alkyne CH lie in a shielded region, and hence alkyne is the least delta value compound. With this I am done with this concept, so we will meet in the next class. Thank you.